Hey friend, welcome. If you have problems falling asleep, you are at the right place. Tonight, we will explore scientific base of major sci-fi concepts. You don't have to stay awake, just relax and let your curiosity fall asleep with you. Chapter 1. From Fiction to Physics, When Imagination Meets the Laws of Nature. Science often begins as a picture in the mind. Before there is data, there is a scene, a vessel gliding between stars, a voice carried without wires, a doorway from here to somewhere distant. Such images are not calculations, yet they guide the questions that later become equations. Physics translates vivid scenes into careful statements about how nature behaves, and then asks nature to judge them. When science fiction lends physics a vision, physics replies with an experiment. Across generations, this exchange has turned wonder into work, and work back into wonder. To ask what is impossible is to ask the universe draws its boundaries. Some impossibilities are logical, like a square circle, and do not concern physics. Others are physical, claims that would violate well-established principles such as conservation, causality, or symmetry. A third kind is technological, where an idea lies beyond current capability but not beyond natural law. It is crucial to keep these categories distinct. Heavier-than-air flight was once considered impossible for practical reasons, not because nature forbade it. Perpetual motion is impossible because nature forbids it. Faster-than-light signaling threatens causal order and therefore stands on the wrong side of physics itself. Distinguishing these boundaries is the first step toward meaningful imagination. Imagination is necessary in science, but it is disciplined. A hypothesis begins as a story about how the world might behave. That story is turned into a model that yields predictions, which are then tested. Experiments confront those predictions, and independent groups repeat them under different conditions. Findings that survive replication earn provisional trust. This cycle is slow because nature is indifferent to enthusiasm. Extraordinary claims require extraordinary evidence, not because scientists are skeptical by habit, but because most tempting ideas fail in the most instructive ways when examined closely. Several principles anchor modern physics. Conservation laws tell us that certain quantities, energy, momentum, charge, remain unchanged when the environment does not favor one place or time over another. This deep link between symmetry and conservation is expressed through Noether's theorem, one of the most beautiful insights in theoretical physics. Causality, the ordered relation between cause and effect, is preserved through relativity. No signal can travel faster than light. Quantum mechanics complicates our intuition, but still respects that structure when information is defined carefully. Together, symmetry, conservation, and causality form a quiet triad against which all new ideas must be tested. Science fiction offers a rehearsal stage where ideas move freely against those constraints. A writer imagines a starship that warps space, a cloak that bends light, or a gate that bridges distant worlds. Physics does not dismiss these visions outright. It asks what resources they would require, what consequences would follow, and which principles must remain intact. Often the first conclusion is that the energy demands are intolerable, or that exotic matter is needed in a form unknown to nature. Yet sometimes the verdict is gentler. A dream survives as a narrow theoretical possibility with extreme conditions attached. Either outcome is valuable. By confronting vision with principle, we learn where creativity meets reality. This dialogue between story and science is older than modern physics. Writers described submarines before engines and materials made them possible. Geostationary satellites were conceived decades before they circled the Earth. The dream of visiting the moon predates the language of orbital mechanics, but inspired those who later derived it. In each case, fiction framed a question, and physics supplied a method. The answers were rarely simple yes or no. They were how, when, and under which laws. Physicists also use imagination, though they call it the thought experiment. A beam of light bouncing between mirrors in a moving box, a pair of clocks carried along different routes, a cat entangled with a quantum trigger. These images distill complex ideas into manageable tests. Though abstract, they are not idle. Lessons drawn from them guide the design of experiments and the interpretation of data. The corridor between imagined scene and measured signal runs both ways. Since this series explores technologies that seem impossible, we must separate what is forbidden by principle from what is merely difficult. Faster-than-light communication would overturn causal order and thus violates relativity. Faster travel by reshaping space itself might avoid direct violation, but requires negative energy densities never observed. Perpetual motion defies the conservation of energy. Teleportation of macroscopic matter contradicts the quantum rule that unknown states cannot be copied perfectly. These limits are not arbitrary. They are the shape of reality revealed through experiment. Yet boundaries can move. New mathematics and finer measurements sometimes expand what was thought impossible. Quantum tunneling revealed how particles cross barriers, enabling nuclear fusion and semiconductor devices. Relativity, once purely theoretical, became practical through technologies that must correct for time dilation, such as satellite navigation. The detection of gravitational waves turned an abstract prediction into a new astronomical sense, letting us hear cosmic collisions. These triumphs did not overturn old knowledge. They refined it. Still, not every extraordinary claim endures. Reports of engines that push against nothing or signals that leap instantaneously across space have dissolved under scrutiny. Apparent free energy devices vanish once every source of energy is counted, including information. These episodes are not failures of curiosity, but lessons in rigor. By disproving what cannot work, physics strengthens what can. Reliable knowledge depends on careful methods. Measurements include uncertainties, instruments drift, expectations bias results. Peer review catches many errors, but replication by independent groups is the true test. The rise of open data and transparent analysis has made correction faster, which is how science earns its credibility. Skepticism is not cynicism, it is a habit of humility before evidence. History shows how bold imagination can survive this discipline. Einstein's relativity began as thought experiments about light beams and trains. Its predictions were tested by measuring starlight deflection during a solar eclipse and later confirmed by precise timekeeping on orbiting satellites. Quantum theory began with questions about black-body radiation and grew into a framework verified by countless experiments from atomic clocks to superconductors. The pattern is clear. Imagination proposes, measurement disposes, what remains becomes knowledge. Ethics also lives at this frontier between fiction and fact. Stories let us explore the human consequences of discovery before they occur. Teleportation raises questions about identity and consent. Time travel provokes reflection on history and responsibility. Invisibility touches on privacy and power. Physics cannot answer moral questions, but by speaking truthfully about what is and is not possible, it helps society discuss those questions responsibly. Modern physics is collective in a way early science could not have imagined. Instruments now span kilometers or orbit in deep space. Teams number in the thousands. This scale magnifies both the promise and the responsibility of new ideas. Announcing an impossible breakthrough can mislead, waste resources, and erode public trust. Guarded optimism, dreaming boldly but proving carefully, is the only sustainable path forward. The topics that follow in this series were chosen because they sit precisely on that edge. Warp drives invite us to reconsider motion itself. What if instead of moving through space, space could move around us? Wormholes tempt us with shortcuts through space-time, though their stability demands exotic matter we have never seen. Time travel exposes how relativity allows curved timelines, while chronology and quantum effects resist paradox. Teleportation explores how quantum information moves without matter. Cloaking devices show how controlling electromagnetic fields might hide an object, though only in limited ranges. Each idea meets nature's strict laws, and in doing so reveals something profound even when the answer is no. Physics does not crush imagination, it orients it. The cosmos is far stranger than our instincts suggest, yet it remains lawful and comprehensible. Within those laws lies space for wonders that need no miracle, for technologies that appear magical only because they obey the rules in subtle ways. When direct paths fail, creative minds search for indirect ones through geometry, probability, or information itself. Fiction gives us courage to ask large questions. Physics gives us the tools to ask them responsibly. So what does impossible really mean in science? It means that within the range we have tested, and to the precision we can reach, a certain phenomenon has never occurred and likely cannot without overturning deeply verified principles. Such revolutions are rare but not impossible. They preserve what worked while expanding what can be explained. Between such leaps, progress continues in smaller, elegant steps. Clearer data, quieter instruments, deeper theories. Those steps, though humble, keep the flame of discovery alive. This first chapter, then, is a compact between wonder and rigor. We will explore ambitious visions, but we will let evidence decide. We will use imagination to frame questions and mathematics to sharpen them. We will rely on knowledge that can be checked and words that mean exactly what they claim. The reward for such discipline is trust, and trust makes awe sustainable. As the series unfolds, remember that the universe is not built to satisfy our stories, yet our stories can sometimes teach us how to listen to the universe. Now, let the mind settle. The same stars that guided our ancestors still trace their quiet arcs above you. The laws of nature keep their silent watch while you rest. Let the weight of the day fall away. Tomorrow's curiosity will still be waiting when you wake. Chapter 2: The Cosmic Speed Limit. Why Nothing Can Outrun Light. Among the most remarkable discoveries in physics is that nature has a built-in speed limit. It is not set by technology or by the strength of engines, but by the structure of the universe itself. That limit is the speed of light in empty space, a constant woven into the geometry of space-time. To understand why nothing outruns light, we must explore how light behaves, how motion is measured, and why the laws of physics look the same for everyone who moves smoothly through the cosmos. In the 19th century, James Clerk Maxwell unified electricity and magnetism and showed that electromagnetic waves travel at a specific speed determined by the properties of the vacuum. His equations predicted that this speed should be the same for all observers, no matter how they move. Experiments that tried to detect any difference in light's speed due to Earth's motion failed repeatedly. The conclusion was startling. Light does not obey the simple rule that velocities add, like walking on a moving walkway. Nature was hinting that space and time themselves behaved differently than we once imagined. Einstein's special theory of relativity began with two postulates. The first, the laws of physics are the same in all inertial frames of reference. The second, light in vacuum moves at a constant speed for all such observers. Together, these principles forced a radical redefinition of how space and time relate. To preserve the constancy of light's speed, clocks must tick at different rates when moving relative to one another, and lengths must contract along the direction of motion. These are not optical illusions. They are real consequences of how space-time keeps the laws of physics consistent for every observer. Relativity divides the universe into regions defined by light cones. Inside each cone are events that can be linked by signals moving at or below light speed. Outside are events that can never be connected without violating causality. This structure ensures that cause always precedes effect in every frame of reference. If a signal could move faster than light, two observers in different states of motion could disagree about which event came first. Reality itself would lose its sense of before and after. The cosmic speed limit is therefore not a technical obstacle. It is the guardian of cause and effect. Massive objects cannot reach light speed because energy and momentum grow without bound as velocity increases. Each push yields a smaller increase in speed, while energy requirements soar. Even the largest particle accelerators, which pour unimaginable energy into subatomic particles, find that their speeds creep ever closer to light's limit, but never reach it. Particles with zero rest mass, like photons, travel at that speed by their very nature. They cannot slow down or stop. Light speed is thus not something to be achieved. It is a property of existence for massless things. Einstein's later theory of general relativity expanded this picture to include gravity. Gravity is not a force in the traditional sense, but a curvature of space-time itself. Objects in free fall follow the straightest possible paths through that curved geometry. Even in this deeper framework, light speed remains the local limit for all motion. Gravity can bend light's path or delay its arrival, but it cannot let anything exceed that boundary. Measurements of signals passing near massive bodies, or of the deflection of starlight during eclipses, have confirmed this with exquisite precision. Everywhere we look, the same limit stands firm. Sometimes the statement, "Nothing can go faster than light," is misunderstood. Light travels more slowly through materials such as glass or water, where it interacts with atoms along the way. A charged particle can move through such a medium faster than light does in that material and emit a faint blue glow known as Cherenkov radiation. Yet it still moves more slowly than light does in vacuum, so no law is broken. The universal limit concerns light in empty space, not its slowed passage through matter. Wave physics brings its own subtleties. In some engineered materials, the phase or group velocity of waves can exceed the vacuum light speed, but this does not mean information travels faster. Only the front velocity, the speed at which a truly new signal begins, carries information, and that always respects the universal limit. causality remains safe, no matter how clever the setup. Quantum mechanics introduces even stranger phenomena. Entangled particles exhibit correlations that seem instantaneous across great distances. One might imagine this as faster-than-light influence, but it is not. The correlations become visible only when the results from both sides are compared later through ordinary, slower-than-light communication. No information or control passes faster than light, and quantum field theory is built specifically to preserve that rule. Observables associated with regions separated by a space-like distance cannot influence one another directly. The universe may be non-local in correlations, but it is still causal in communication. Theories that try to move beyond relativity often begin by asking whether the limit could be bypassed rather than broken. The idea of a warp drive, for example, imagines contracting space in front of a spacecraft and expanding it behind, so that the craft itself never locally moves faster than light, but the distance between origin and destination shrinks. Similarly, traversable wormholes are hypothetical tunnels through space-time that could link two distant regions directly. General relativity's equations do permit such solutions, but maintaining them requires exotic matter with negative energy density, something never observed in stable form. Quantum effects can produce brief, tiny negative energies, but known physical limits make them far too small to support macroscopic warp bubbles or wormholes. The mathematics is intriguing. The engineering remains impossible. Another apparent exception arises in cosmology. Distant galaxies recede from us faster than light as space itself expands. Yet this too does not violate relativity. The galaxies are not moving through space faster than light. Rather, the metric that defines distances between them is stretching. Locally, every observer still measures light moving at the same invariant speed, and no object ever overtakes a nearby light beam. The speed limit is a local law, bound to the light cones that define causality, even in an expanding universe. Evidence for this principle appears everywhere. Satellite navigation systems must correct their onboard clocks for both special and general relativistic effects. Without accounting for time dilation, their timing errors would accumulate rapidly and destroy positional accuracy. Particle accelerators confirm the limit each time their beams refuse to reach the forbidden speed, no matter how much energy is added. Astronomical observations show that gravitational waves and light from the same cosmic events arrive almost simultaneously, proving that both propagate at the same universal speed. From laboratory to cosmos, the same constant quietly rules the flow of information and energy. It is sometimes asked whether faster-than-light particles, called tachyons, might exist. In consistent quantum field theories, a tachyonic term indicates instability rather than true superluminal motion. The system simply rearranges itself into a stable configuration where all real excitations move slower than light. In this sense, tachyons are mathematical warnings, not real travelers through space-time. Over a century of experiment has found no evidence for any particle that carries information faster than light, and relativity continues to describe all observed phenomena with extraordinary accuracy. Accepting the cosmic speed limit is not a surrender of imagination. It is an invitation to creativity. Knowing that nothing can cross this boundary encourages scientists and storytellers to think differently about travel and communication. Astronomers work with a light that has taken billions of years to reach us, turning delay into a window on the past. Engineers use gravitational assists and precise navigation to make the most of limited speed. Theorists explore how the structure of space-time might one day allow shortcuts without breaking the rules. Even fiction adapts, using the limit to create stories where patience, strategy, and isolation replace instant motion. Constraint becomes a source of meaning. Light's constant speed is far more than a number. It is a fundamental feature of the universe. It connects space and time in a single fabric and defines how energy relates to mass. It governs how electromagnetic waves propagate and how causality remains intact. The same constant appears in the equations of relativity, electromagnetism, and quantum field theory. It is not merely the speed of light. It is the heartbeat of the cosmos, the rhythm that keeps every observer's version of reality consistent with every other's. Understanding this limit brings perspective. When we look up the night sky, the starlight that reaches us tonight began its journey long before our species existed. It has obeyed the same cosmic rule across unthinkable distances, arriving calmly, faithfully, without haste. The universe does not rush, and it never forgets its own order. So, as this day ends, let that constancy quiet the mind. The same speed that binds galaxies and photons also connects every moment you live. Breathe slowly. The light will keep traveling, steady and sure, across the silent fabric of space, waiting for you to meet it again when morning comes. Chapter 3. Warp Drives. Bending space instead of breaking it. The dream of faster-than-light travel has always been one of humanity's boldest imaginings. For centuries, it existed only in stories. Vessels that crossed galaxies in moments, civilizations connected by corridors of distorted space. When the theory of relativity declared that no object could move through space faster than light, many assumed that dream was gone forever. But some physicists began asking a more subtle question. What if the limit applied only to motion through space? What if space itself could move? This is the foundation of the warp drive concept. Instead of propelling a ship faster than light in the usual sense, a warp drive would reshape the space-time around it. The craft would sit inside a region of locally flat space, a bubble, while space ahead of the bubble contracted and space behind it expanded. The ship itself would remain still relative to the bubble, never locally breaking the light speed limit. Yet the bubble could, in principle, move faster than light relative to distant observers. In this way, the vessel would not move through space but would move with space itself. The first serious mathematical description of such a drive came in the mid-1990s when Mexican physicist Miguel Alcubierre proposed a space-time metric based on Einstein's equations that allowed precisely this arrangement. In his model, space could be made to contract in front and expand behind, creating a traveling region that carried anything inside it along. The equations showed that relativity did not forbid such a geometry. There was no violation of the light speed limit because, locally, the ship never exceeded that speed. Yet the concept was not a free pass to interstellar travel. The equations demanded a form of energy very different from anything we know: negative energy density. In ordinary matter, mass and energy curve space-time in a positive way, producing gravitational attraction. Negative energy would curve space-time in the opposite way, creating a repulsive effect. Quantum physics predicts that in certain rare situations, such as the Casimir effect between closely spaced metal plates, small regions of negative energy can arise temporarily. But these effects are tiny and fleeting, far too weak to create or sustain anything like a warp bubble. Alcubierre's calculations suggested that to move a modest spacecraft, one would need negative energy equivalent to the mass energy of an entire star. Later refinements reduced the number somewhat, but the requirements remain well beyond anything conceivable with known physics. Even if one somehow obtained negative energy, further problems emerge. The boundary of the bubble, where space is stretched and compressed, forms a region with extreme tidal forces. Any matter there would be torn apart by gradients of gravity. Communication with the outside world would also be impossible while the bubble moved faster than light relative to its surroundings, because no signal could travel from the ship to the front of the bubble. That means the crew could not steer or stop once the warp was engaged. To exit the bubble, one would have to plan its entire path before departure and hope that the equations describing it held exactly true. Researchers who followed Alcubierre's work explored modifications that might make the idea less demanding. Some proposed warp fields with smoother gradients to reduce energy costs. Others looked into Notario drives, in which space is distorted without explicit expansion or contraction, hoping to eliminate the need for exotic matter. In every case, the same obstacle returns. General relativity itself permits these geometries, but quantum field theory, our best understanding of energy, severely limits how negative energy can exist. Quantum inequalities developed by Ford and Roman show that negative energy cannot be both large and long-lasting. It appears in tiny amounts and vanishes quickly, balancing out so that the universe's overall energy remains positive. This interplay between general relativity and quantum theory is the crux of modern physics. Relativity describes the grand shape of space-time. Quantum theory describes its smallest vibrations. Warp drives sit precisely at their intersection, the place where our current theories do not fully agree. Physicists often say that a complete theory of quantum gravity would be needed to know whether a warp bubble could truly form. Until such a theory exists, warp drives remain mathematical curiosities, not engineering projects. Still, the idea has scientific value. It highlights that relativity does not ban superluminal effects. It only bans local superluminal motion. The expansion of the universe itself shows this principle at work. Distant galaxies recede from us faster than light because the space between us stretches, not because they move through it faster. Inflationary cosmology proposes that, in the first instant after the Big Bang, the universe expanded exponentially, carrying regions apart far faster than light could travel between them. In that sense, the cosmos performed its own warp drive on a universal scale. This insight reshapes how we think about travel. Instead of fighting the laws of physics, we might someday learn to use them, guiding space-time's own flexibility the way a surfer rides a wave. It is an appealing metaphor, but one with limits. To surf a cosmic wave, one must first create it, and that remains beyond any known mechanism. The energy locked in even a small amount of space-time curvature is immense. The gravitational field of Earth itself, though gentle, represents an energy density far greater than we could hope to manipulate directly. The vacuum is not empty. It is a field filled with quantum fluctuations that average to zero only when left undisturbed. Bending that structure on purpose would require technology more advanced than anything we can yet define. Despite the physical obstacles, the concept of a warp drive has stimulated genuine scientific work. NASA's EagleWorks laboratory and other small research groups have investigated whether tiny fluctuations in quantum fields could, under special configurations, mimic the mathematics of a warp field. Their experiments so far have not detected any real effect, but even negative results refine the boundaries of what is possible. Some physicists have explored analog systems, using fluid dynamics or metamaterials to simulate how space-time might behave near a warp bubble as a way to understand the geometry experimentally. Others examine whether the energy requirements could, in theory, be balanced using dark energy, the mysterious component that drives cosmic acceleration. These studies are not attempts to build starships today, but exercises in understanding how the universe's fabric might respond to extreme manipulation. They reveal that Einstein's equations allow far more variety than nature usually displays. Most of those varieties require conditions the universe rarely provides, but by exploring them, we learn how far the laws can be stretched before they break. This is the same reasoning that drives research into black holes, wormholes, and cosmic strings, objects that test the limits of spacetime's flexibility. An important subtlety often missed in popular discussions is that spacetime curvature is not a material thing to be pushed or molded like clay. It is a relationship between matter, energy, and geometry. To bend space, one must redistribute energy in such a way that the geometry responds accordingly. Energy itself is constrained by conservation laws and quantum behavior, so even in principle, control would be delicate. The dream of warp travel therefore serves as a mirror, showing both our imaginative reach and our physical humility. In recent years, computer simulations of Alcubierre-type metrics have become more detailed. They show that, while the equations are consistent within general relativity, the transition regions of a moving warp bubble would likely emit intense radiation and gravitational disturbances. These would destroy any nearby matter long before the bubble reached superluminal speeds. Even a stationary bubble would collapse quickly once its exotic energy supply ended. The mathematics may allow a brief pulse, a warp wave, but not a stable, sustained drive. The same equations that permit the possibility also guard against its misuse. There is a quiet lesson here about how physics balances imagination and reality. The laws of nature do not seem cruel. They seem consistent. Every new idea must harmonize with those laws or risk dissolving into fantasy. Warp drives remind us that the universe is not a playground without rules, but a deep structure where even impossibility has a logic. By examining that logic, we expand the frontier of understanding, even if the dream remains beyond reach. And yet, something about the idea persists. Perhaps it is because space-time itself feels alive in the equations, elastic, responsive, almost mindful. The notion that we might one day learn to ride that fabric speaks to a deeper hope, that intelligence is not merely trapped within the cosmos but part of its unfolding design. If the universe once inflated faster than light, perhaps it is telling us that boundaries are not absolute, only contextual. At its heart, the warp drive is not about escaping physical limits. It is about exploring how flexible those limits truly are. It challenges us to imagine responsibly, to dream in equations, not just in images. For now, no evidence suggests that a warp bubble could ever be realized. Yet by studying such impossible ideas, we often uncover new insights into gravity, quantum fields, and the structure of the vacuum. Impossibility in science is rarely a dead end. It is an arrow pointing toward what we do not yet understand. So when you hear of ships bending space to cross the stars, remember that the physics behind them is not pure fantasy, but an invitation to think deeper about the nature of distance and motion. The universe already warps and stretches. We are simply learning to read its movements. Even if no human vessel ever folds space-time around itself, the act of contemplating it connects us to the same curiosity that drives every scientific discovery. Close your eyes for a moment and imagine that vast geometry, not a map of destinations, but a living fabric that breeds expansion and contraction. Somewhere within it, you are moving with the Earth, with the Sun, with the galaxy itself, carried gently by the curvature of space-time. There is no need to rush. The universe already flows, and you are part of its quiet current. Chapter 4. Wormholes, shortcuts through the fabric of reality. Among all the ideas born from the marriage of physics and imagination, few capture the mind like the wormhole. A tunnel through space and time, a doorway that might connect distant galaxies or even different universes. It is a concept that feels both elegant and improbable. Yet wormholes are not inventions of science fiction alone. They emerge naturally from the mathematics of general relativity, Einstein's great description of how matter and energy shape the geometry of space-time. In this theory, gravity is not a force, but a curvature, and under the right conditions that curvature can fold back upon itself, forming a bridge between otherwise separated regions of the cosmos. The earliest form of such a bridge appeared shortly after Einstein published his equations. In the late 1930s, physicists Albert Einstein and Nathan Rosen examined a mathematical solution that seemed to link two regions of space-time through a throat-like connection. They imagined it as a single entity, what we would now call a non-traversable wormhole. The structure, known as the Einstein-Rosen bridge, connects two black hole-like regions but pinches off so quickly that nothing, not even light, could travel through. The tunnel collapses faster than any signal could cross it, sealing both ends behind event horizons. This model showed that wormholes were possible in principle, but not in practice. Decades later, in the 1980s, physicists Kip Thorne and Michael Morris revisited the idea and asked a daring question. Could a wormhole exist that stays open long enough for something, perhaps even a person, to pass through? Using general relativity, they found that, mathematically, it could. But there was a catch. Just as with the warp drive concept, an open wormhole required a kind of negative energy to keep its throat from collapsing. Ordinary matter has positive energy density and exerts gravitational attraction, but a wormhole throat would need something that curves space-time in the opposite direction, effectively resisting the squeeze of gravity. Quantum field theory does allow for small, fleeting amounts of negative energy, such as those observed in the Casimir effect, a subtle force that arises between two closely spaced metal plates in a vacuum. However, these effects are minuscule and vanish almost instantly. To sustain a traversable wormhole large enough for even a photon to pass through, the amount of exotic energy needed would be astronomical. Moreover, quantum inequalities restrict how long and how strongly negative energy can exist. The universe seems to allow such anomalies only briefly, as if it permits the concept for mathematical completeness, but forbids its practical use. Wormholes, then, live at the intersection of relativity's flexibility and quantum mechanics' strict bookkeeping. Relativity's equations are generous, They allow space-time to twist, bend, and even connect in unusual ways. But quantum theory enforces limits on the kinds of energy that can exist. Whenever physicists try to join the two in extreme conditions, paradoxes emerge. Some theoretical physicists have speculated that in a full theory of quantum gravity, wormholes might appear naturally as microscopic phenomena, fleetingly connecting points in space at subatomic scales. These quantum foam wormholes would be unimaginably tiny and vanish almost as soon as they appear, playing no role in large-scale travel, but perhaps contributing to the quantum structure of space-time itself. In the 1990s, interest in wormholes deepened again when researchers noticed that quantum entanglement, the strange correlation that links particles across distance, might share mathematical similarities with wormholes. This connection has grown into what is now called the EPR conjecture, an idea suggesting that every pair of entangled particles might be linked by a tiny, non-traversable wormhole. In this view, wormholes are not cosmic highways, but geometric representations of quantum connections. They would not allow travel or communication, but they might reveal how space-time itself emerges from networks of entanglement. The proposal remains speculative, but has influenced many lines of research in quantum gravity and information theory. Wormholes also provide a fascinating test bed for exploring time and causality. If one end of a traversable wormhole were accelerated to relativistic speed and then returned to rest, time dilation would cause the two ends to become desynchronized. In principle, this could turn the wormhole into a time machine, allowing a traveler to move between the mouths and emerge at a moment earlier than they departed. The possibility raises profound paradoxes, events that could cause themselves or prevent their own origin. Many physicists suspect that nature prevents such scenarios through mechanisms that preserve chronology. Stephen Hawking proposed what he called the chronology protection conjecture, suggesting that quantum effects would destabilize any wormhole that could be used for time travel, closing the path before paradoxes arise. Even without time travel, the practical difficulties of building or finding a wormhole are immense. To hold a throat open, one must counteract not only the gravitational collapse, but also the vacuum fluctuations of quantum fields that would tend to destabilize it. A traversable wormhole would emit intense radiation from tidal forces and quantum particle production near its mouth. The slightest perturbation could cause it to collapse into a black hole. No known natural process produces stable wormholes, and observational searches have found no evidence of them. The closest candidates, black holes themselves, show no hint of hidden exits. Every signal that falls into a black hole disappears behind an event horizon, never to emerge elsewhere. Still, wormholes remain powerful tools for theoretical exploration. They challenge our understanding of locality, the idea that objects can influence only their immediate surroundings. In quantum mechanics, entanglement already blurs locality, and wormholes push that blurring into the geometry of spacetime itself. They also offer insight into the nature of information. If information falling into a black hole is preserved rather than destroyed, as quantum theory demands, perhaps it escapes through subtle correlations that act like microscopic wormholes. In this way, the wormhole becomes a metaphor for information conservation in a universe where nothing is ever truly lost. Although wormholes may never become physical portals for travel, their study enriches our understanding of the cosmos. They encourage physicists to ask daring questions. What is the true texture of space and time? Is distance a fundamental feature of reality, or an emergent one that arises from deeper connections? Could the universe itself be a vast web of relationships where geometry and information are two sides of the same coin? Such questions reach beyond engineering and touch philosophy, where the boundaries between physics and meaning blur. It is also possible that wormholes play a quiet role in cosmology. Some models suggest that the universe might have formed through a quantum tunneling event that connected two regions of a larger multiverse. In that context, the Big Bang could be seen as the mouth of a gigantic wormhole opening into our observable cosmos. Other researchers have explored whether wormholes could serve as shortcuts through space-time for cosmic strings or magnetic fields, influencing the large-scale structure of the universe. None of these ideas are confirmed, but they show how fertile the wormhole concept has become for modern physics. Mathematically, wormholes are beautiful because they show how geometry can mimic topology. They illustrate that space-time is not simply a stage where matter moves, but an active participant in the drama of existence. When you imagine two distant points in the universe connected by a smooth tunnel, you are imagining space-time not as emptiness, but as something that can twist and fold. This flexibility is the essence of general relativity. The insight that space and time are dynamic, responsive, and alive with curvature. As with the warp drive, the real value of the wormhole lies not in the fantasy of instant travel, but in what it teaches us about physical law. The idea pushes scientists to test the limits of energy conditions, explore quantum corrections to gravity, and seek a unified theory that reconciles relativity and quantum mechanics. Even if wormholes remain forever theoretical, the effort to understand them brings us closer to answering questions about how the universe is stitched together. The bridge may never open, but by studying its architecture, we learn more about the fabric we already inhabit. And there is something deeply human about that pursuit. To imagine a wormhole is to express the desire to connect, to reach beyond distance, time, and isolation. It mirrors the way consciousness itself seems to bridge vast gaps between past and present, self and cosmos, thought and matter. The same curiosity that draws us to stars also drives us to explore the unseen geometry between them. In a way, the longing for wormholes reflects our longing to overcome separation, to find unity in a universe that appears vast and cold. Perhaps the true shortcut is not a tunnel through space-time, but an understanding that distance is relative, that every particle, every mind, and every moment shares the same underlying reality. Wormholes may never carry us across galaxies, but they already connect our imagination to the fundamental mystery of existence. In their shadow, we see that space itself is not an obstacle, but a question. How deeply can connection be defined? As you drift toward rest, imagine the universe as a single continuous surface, folding and unfolding in endless harmony. Somewhere in that fabric, countless paths cross invisibly, not as tunnels for travel, but as quiet reminders that separation is never absolute. The stars above you, distant though they seem, are part of the same cosmic web that holds you now. The universe connects everything already. You only need to feel its stillness to know that you have never truly been far from anything at all. Chapter 5. Time Travel and Temporal Paradoxes. Few ideas in physics stir the imagination as powerfully as time travel. It touches the deepest part of human curiosity, the longing to revisit the past, to undo regret, to see the far future before it arrives. In fiction, time travel is a narrative bridge across eras, but in physics, it becomes a question about the nature of causality itself. What does it mean to move through time in a direction other than forward? Does the universe even allow such motion? Or is time's arrow an unbreakable one-way law? To explore these questions, we must begin with relativity. Einstein's special theory revealed that time is not universal. The flow of seconds depends on motion and gravity, linking time and space into a single four-dimensional structure called space-time. A moving clock ticks more slowly than one at rest relative to an observer, and a clock near a strong gravitational field ticks more slowly than one farther away. This phenomenon, known as time dilation, has been measured repeatedly in high-speed aircraft, in satellites, and in subatomic particles moving close to light speed. These effects are small at ordinary speeds, but they prove that time's rhythm is flexible. This flexibility creates a real physical kind of time travel into the future. Astronauts orbiting Earth age slightly less than those on the surface. Particles moving near light speed live longer than their stationary counterparts. This form of travel cannot be controlled beyond the natural effects of motion and gravity, but it demonstrates that time is not absolute. In this limited sense, every space traveler becomes a time traveler. The more controversial question is whether travel into the past is possible. General relativity, which describes gravity as space-time curvature, contains solutions to its equations that seem to allow it. One such solution, discovered by the mathematician Kurt Gödel in the mid-20th century, describes a rotating universe where time loops back upon itself. In Gödel's model, an object could, in principle, follow a path through space-time that returns it to its own past, a closed time-like curve. Similar curves appear in theoretical models involving rotating massive cylinders, wormholes, and warp-like geometries. In each case, the equations do not forbid time travel outright. They simply require exotic conditions, such as immense rotation or negative energy, to make it work. However, theoretical possibility and physical plausibility are very different things. A spacetime that allows closed time-like curves also challenges the concept of causality, the simple order of cause and effect. If a traveler could go back and alter an event, what would prevent contradictions? The classic example is the grandfather paradox. If you travel to the past and prevent your grandparents from meeting, then you would never be born, and therefore could not have made the journey to interfere. Physics demands consistency, but the logic of time travel seems to create impossible loops. Physicists have proposed several ways to address such paradoxes. One is the Novikov self-consistency principle, which states that events on a closed time-like curve are self-consistent. In other words, whatever happens must be compatible with history as it already exists. If you traveled back in time, you could not change the past. Your actions would always turn out to have been part of it. The paradox resolves itself through inevitability. You might attempt to prevent your grandparents meeting, but circumstances would always conspire so that you fail, or, paradoxically, cause the meeting to happen in the first place. This principle preserves consistency, but at the cost of free will, suggesting that time's fabric enforces its own coherence. Another possible resolution arises from quantum mechanics. The many worlds interpretation proposes that every quantum event with multiple outcomes causes the universe to branch into separate realities, each containing one result. Under this view, a traveler who goes back and changes the past would not alter their own history, but would create or enter a parallel timeline where their new actions hold true. In that case, no paradox arises because both versions of reality coexist. The original timeline remains unchanged. The traveler simply moves into another branch. Though elegant in theory, this solution raises difficult questions about the physical meaning of branching universes and the mechanism by which transitions occur. Physicists such as Stephen Hawking doubted that time travel into the past is physically possible, proposing instead what he called the chronology protection conjecture. It suggests that quantum effects near the formation of a time loop would produce intense energy fluctuations that destroy the loop before it could form. In essence, the laws of physics themselves would act as guardians of causality, sealing off any route to the past. Hawking once joked that if time travel were possible, we would already be overrun by tourists from the future. And since we are not, nature must have found a way to forbid it. Even so, the universe contains hints that time is not as rigid as our experience implies. In quantum field theory, the vacuum itself teems with fluctuations, particles appearing and vanishing within intervals so brief that they borrow energy from the future and repay it almost instantly. On these microscopic scales, the distinction between past and future blurs. Quantum mechanics does not require a global arrow of time. It requires only consistency in probabilities. Some physicists suspect that the arrow of time, the sense of flow we experience, emerges from entropy, the measure of disorder. In a universe that began in an extraordinarily ordered state, entropy increases naturally, and we perceive that increase as time moving forward. If entropy were ever to decrease universally, the arrow might reverse. But such a reversal would be thermodynamically improbable, not physically forbidden. Black holes add another layer of complexity. Their extreme gravitational fields slow time dramatically for anything near the event horizon. A distant observer would see an object approaching the horizon freeze in time, while the object itself would experience only moments passing before falling inward. This asymmetry suggests that time can stretch to near infinity under the right conditions, effectively freezing a moment forever from the outside perspective. Yet even here, causality remains intact. Information cannot escape faster than light, and no true reversal of time occurs. Despite its implausibility, the idea of time travel has deep scientific utility. It serves as a thought experiment for testing the limits of relativity and quantum theory. When physicists analyze hypothetical time machines, they uncover insights about energy conditions, quantum gravity, and the structure of space-time. These studies often reveal that what seems fantastical at first illuminates where our theories break down. For example, attempts to model a stable time machine almost always require exotic energy densities that violate known physical laws. In that sense, time travel operates as a diagnostic tool. It shows us where the boundary between mathematics and nature lies. Time travel also raises profound philosophical questions about identity and existence. If the future is already written in the equations, does free will exist at all? If multiple timelines are real, what defines continuity between versions of the same person? Even without physical time machines, these questions remind us that our experience of time is subjective. The brain constructs a sense of now by integrating sensory information with memory and anticipation. In that light, every mind already performs a kind of temporal navigation. constantly weaving the past into the present to project itself into the future. Physicists studying quantum information have discovered that, in some mathematical formulations, sending quantum data backward in time produces results that resemble teleportation rather than paradox. These models do not permit communication with the past, but show that certain correlations can simulate retrocausality without breaking consistency. They reinforce the idea that time, in quantum theory, is not an independent backdrop, but part of a network of correlations. The more deeply we examine time, the less it seems like a flowing river, and the more it appears as a landscape in which all events coexist, with the illusion of movement arising from our limited perspective. In modern cosmology, time may not have a clear beginning or end. Some models suggest that before the Big Bang, there could have been another contracting phase, a mirror universe running in the opposite temporal direction. In such a framework, what we call the past and the future might be relative directions within a larger, symmetric cosmos. This speculation, though untested, resonates with the idea that time's arrow is an emergent feature, not an ultimate rule. Ultimately, physics has not found a way to break time's barrier. It may be that causality is too deeply woven into the structure of reality to be undone. But the search for loopholes, in wormholes, in quantum mechanics, in cosmology, continues to sharpen our understanding. Each attempt to imagine time travel forces us to clarify what time actually is. Is it a dimension like space, waiting to be navigated, or a process that emerges only in the presence of change? The fascination with time travel is therefore more than fantasy. It is a reflection of how we relate to existence itself. To live is to move through time, and to wish to move otherwise is to question the limits of being. The past shapes identity, the future fuels hope, and the present is the narrow bridge between them. Time travel stories echo our yearning to escape loss, to correct mistakes, or to glimpse meaning beyond the moment. Perhaps physics will one day find that time is not as linear as it appears, that the universe holds deeper symmetries beyond our current perception. But even if the past remains unreachable, its traces are here, in the starlight crossing space for eons, in fossils beneath our feet, in the memories carried by every human mind. In that sense, we already live among the ghosts of earlier moments, moving within a cosmic memory that never truly fades. As night deepens, consider that you are already a traveler in time, carried forward at 1 second per second by the silent machinery of the cosmos. Each breath marks another small step into the future. The stars above you are messages from the past, and your awareness, brief as it is, belongs to both. You cannot return to where you have been, yet everything you were remains written in the unfolding fabric of time. Perhaps that is enough to move onward through the unknown, knowing that the journey itself is the only direction the universe allows. Chapter 6. Quantum Teleportation, the Real Science of Instant Transfer. The word teleportation evokes images of science fiction, shimmering lights, dissolving bodies, and instant journeys between distant places. Yet in the quiet world of quantum physics, teleportation is not fantasy. It is a real, measurable process. It does not move matter from place to place, but rather transfers information about the deepest state of that matter. What travels is not the particle itself, but the blueprint of its quantum identity, recreated somewhere else, while the original version ceases to exist in its former form. To understand quantum teleportation, we first need to grasp how strange quantum information truly is. In classical physics, an object can be described completely by listing its measurable properties: position, momentum, temperature, color. In the quantum realm, things are different. A single particle can exist in a superposition of possibilities, with outcomes that remain undefined until measurement. The state of such a particle contains all the probabilities of what it could become. Copying that information perfectly is forbidden by one of the fundamental laws of quantum mechanics, known as the no-cloning theorem. It tells us that if we try to duplicate an unknown quantum state, we inevitably disturb it. This rule ensures the uniqueness of quantum information, a kind of cosmic safeguard that prevents simple replication of the universe at its smallest scales. Teleportation works not by cloning but by transferring. The process uses a remarkable phenomenon called quantum entanglement, where two particles become linked so completely that measuring one instantly determines the state of the other, no matter how far apart they are. Entanglement is not communication in the ordinary sense. It is correlation built into the structure of reality. When two particles are entangled, their joint state must be described as a single, inseparable system. Even if separated by light years, they behave as if connected by an invisible thread outside space and time. In a typical quantum teleportation experiment, a sender and a receiver share a pair of entangled particles. The sender then interacts the particle they want to teleport with their half of the entangled pair, performing a special type of joint measurement known as a Bell state measurement. This act destroys the original state of the particle, but encodes its information into the combined system. The sender then transmits the result of this measurement, just two classical bits of information, to the receiver through an ordinary communication channel. Once the receiver applies the corresponding operation to their entangled particle, it assumes the exact quantum state that the original particle had before the measurement. The state has effectively been transferred, though no matter or energy has traveled faster than light. The original particle's state is gone. It has been perfectly reconstituted elsewhere. The beauty of quantum teleportation is that it obeys every rule of physics while performing something that looks impossible. It transfers a state instantaneously in principle, but requires classical communication to complete the process, ensuring that no usable information moves faster than light. In this way, teleportation reconciles the interconnectedness of quantum systems with the causal order demanded by relativity. It is a dance between correlation and communication, between what is instantaneous and what must wait. Experiments have confirmed quantum teleportation repeatedly since the 1990s. Scientists have teleported the states of photons across optical fibers, through free space between mountain peaks, and even between satellites and ground stations in orbit. The distances continue to increase, but the principle remains unchanged. What moves is not the particle, but its quantum description. These experiments demonstrate how entanglement can serve as a bridge for information, a kind of invisible channel through which nature reproduces its own states. Quantum teleportation is also the foundation of emerging quantum technologies. It is a key ingredient in the design of quantum networks, systems that could one day connect quantum computers across great distances. Such a network would not send raw qubits through cables like classical data. Instead, it would distribute entangled pairs between nodes, allowing states to be teleported securely from one machine to another. Because any attempt to eavesdrop on entangled systems disturbs them, quantum teleportation offers a level of security that no classical encryption can match. It represents not just a technological milestone, but a new architecture for communication, one where the universe itself becomes part of the information channel. The implications reach beyond engineering. Teleportation challenges our intuitions about identity and continuity. When a quantum state disappears in one location and reappears in another, is it the same entity or a perfect copy? In the microscopic world, such questions are formal and abstract. But if we imagine scaling the process up, hypothetically transferring the quantum state of a human being, the philosophical consequences become profound. Would the reassembled person still be the original self, or only an indistinguishable replica, the old version effectively destroyed? Physics cannot answer this question. It only describes what happens mathematically. Yet it reminds us that identity itself may be a pattern rather than a substance, a continuity of information rather than the persistence of material atoms. Teleportation also deepens our understanding of entanglement as a physical resource. In classical physics, information can be copied endlessly without cost. In quantum physics, information and energy intertwine in subtle ways. Entanglement must be generated, preserved, and consumed to perform teleportation. When the entangled pair is used, it is spent, its connection lost. This exchange mirrors a deeper truth. To transmit order in one place, we must pay with disorder somewhere else. Entropy, the measure of uncertainty, becomes the hidden currency that underwrites every transfer of information in the cosmos. Recent experiments continue to explore teleportation at larger scales and in different physical systems. Photons, trapped ions, atomic ensembles, and superconducting circuits. Each platform brings its own challenges. Quantum coherence is fragile. Interaction with the environment quickly destroys it, a problem known as decoherence. To achieve reliable teleportation, physicists must isolate particles from noise and maintain entanglement long enough for classical communication to arrive. Progress has been steady, and teleportation has already become a standard tool in laboratories studying quantum networks and computation. Perhaps the most intriguing aspect of teleportation is its role in quantum theory's unification with gravity. In some approaches to quantum gravity, information plays a fundamental role in shaping space-time itself. Theorists have found that the mathematics describing teleportation has a counterpart in the geometry of wormholes. In this analogy, sending quantum information through an entangled pair is like passing it through a microscopic, non-traversable wormhole connecting the two particles. Nothing truly moves through space, but the result appears as if it did. This connection between entanglement, teleportation, and geometry suggests that space-time may not be a background stage at all, but a network of relationships built from quantum information. If that vision proves true, teleportation would not merely be a technological trick. It would be a glimpse into how the universe computes its own existence. The act of transferring a quantum state might reflect the same processes by which space-time keeps distant regions coherent. It would mean that information, not matter or energy alone, is the deepest layer of reality. And yet, even at this frontier, the same principle holds. Nothing breaks causality. Quantum teleportation respects the cosmic speed limit, requiring ordinary communication to finalize the transfer. entanglement alone cannot send a message. What it provides is structure, the scaffolding on which classical signals can weave a coherent whole. This subtle interplay shows that even the most exotic phenomena ultimately preserve the consistency of the physical world. The universe, for all its strangeness, remains orderly in its own language. From a human perspective, teleportation invites reflection on what it means to be connected. Two particles that share no physical link can still behave as one. Perhaps this is a lesson beyond physics, that separation may be an illusion of distance, while connection is woven into the fabric of being itself. Entanglement reminds us that everything in the universe once shared the same cosmic origin, born from a single state of extreme density and unity. In that sense, the correlation seen in quantum systems is not unnatural but ancestral. It is the echo of a time when all things were one. Quantum teleportation, then, is more than a technical process. It is a window into that unity. It shows that reality is not a collection of isolated parts, but a system of relationships, bound together by the invisible logic of information. Each act of measurement, each exchange of data, each entangled pair is a whisper from the underlying order that holds the universe together. So as you drift toward rest, imagine the quiet journey of a photon's quantum state, disappearing in one place and reappearing in another, not as a miracle but as a statement of how the universe shares itself. The same continuity that links two particles across light years links every atom in your body to the stars. Nothing truly vanishes. It only changes its form of description. In a cosmos built on entanglement, every point touches every other in ways we cannot yet see. And perhaps that is what teleportation truly teaches. That distance, time, and separation are only the surface patterns of something far more connected beneath. Chapter 7. Cloaking and Invisibility, the Art of Controlling Light. The dream of invisibility has haunted the human imagination for as long as stories have been told. From ancient myths of gods who vanished at will to modern tales of scientists bending light around themselves, the idea has always seemed like pure fantasy. Yet physics, as it often does, finds a way to turn imagination into experiment. What once belonged to magic now rests in the language of optics, materials science, and electromagnetic theory. True invisibility, the perfect concealment of an object from detection, remains beyond our current reach, but the path toward it has become surprisingly clear. To understand how invisibility might work, we must first understand light itself. Light is not merely illumination. It is a wave of electromagnetic energy that interacts with matter in precise ways. When light encounters an object, part of it is absorbed, part reflected, and part refracted. These interactions produce the information our eyes or instruments use to identify the object's shape, color, and position. To make something invisible, one must guide light around it so that it reemerges as though nothing were ever there. The observer should see not the object, but what lies behind it, a seamless continuation of the background. For centuries, invisibility was thought impossible because light seemed to travel only in straight lines. But the modern study of electromagnetic fields revealed that space can bend light naturally. Gravity itself, as Einstein showed, curves space-time, causing starlight to arc around massive bodies. On a smaller scale, refraction, the bending of light as it passes from one medium to another, allows lenses to focus images and mirages to shimmer on hot roads. The key insight of modern cloaking research is that if gravity and materials can already redirect light, perhaps we can design substances that control it deliberately. This idea took form in the early 21st century with the rise of metamaterials, artificially structured substances engineered to manipulate electromagnetic waves in ways natural materials cannot. Metamaterials are built from repeating patterns smaller than the wavelength of light they affect. These tiny arrangements, often metallic or dielectric, interact with electromagnetic fields to produce effective optical properties not found in nature. By carefully designing their structure, scientists can control how light moves through them, bending it around an object as water flows around a stone. The mathematical framework behind this is called transformation optics. It treats light paths as geodesics, the natural lines that light follows through space, and asks how space could be reshaped to guide those lines around a region. The material parameters required to achieve that guidance are then derived, describing how to construct a medium where light behaves as though space itself were warped. When such a metamaterial surrounds an object, light entering the cloak curves smoothly around it and reemerges on the other side unchanged, rendering the object effectively invisible within a specific range of wavelengths. The first practical demonstrations of cloaking appeared not in visible light, but in microwaves, where wavelengths are longer and easier to manipulate. Researchers created small cloaks that could hide objects about the size of a coin. The results were striking. Microwaves flowed around the hidden object, leaving almost no trace in the detected field. Later experiments extended the technique to infrared and visible wavelengths, though only for tiny scales and narrow color ranges. True broadband invisibility, covering the full spectrum of visible light and working from all viewing angles, remains a distant goal. The limitations arise from the physics of the materials themselves. To bend light across a wide range of frequencies, a cloak must have optical properties that change precisely with wavelength, something extremely difficult to engineer. Many metamaterials also absorb or scatter some light, producing faint distortions that reveal the hidden object's presence. Moreover, metamaterials are inherently fragile. Their fine structures can be disrupted by heat, vibration, or small manufacturing imperfections. For now, invisibility works best in carefully controlled laboratory conditions, under specific frequencies, and for objects far smaller than everyday scale. Still, progress continues. Scientists are exploring plasmonic cloaks that use metallic surfaces to cancel out the scattering of light from an object, and carpet cloaks that conceal bumps or irregularities by reflecting light as if from a flat surface. Others work with photonic crystals and dielectric composites to manipulate infrared radiation for thermal cloaking, making objects invisible to heat sensors. These devices do not hide objects perfectly, but they demonstrate how flexible the control of electromagnetic waves has become. Invisibility has also moved beyond optics. Similar principles apply to sound, water waves, and even elastic vibrations. Acoustic cloaks can steer sound around an object, creating zones of silence. Seismic cloaks are being studied to redirect earthquake waves around structures. Each of these relies on the same idea, that by tailoring the medium through which waves travel, one can determine how the waves interact with what lies inside. The lesson is profound. Invisibility is not about erasing existence, but about mastering the conversation between matter and energy. From a scientific perspective, the pursuit of invisibility is less about hiding and more about control. To make something invisible, one must understand light deeply, its oscillations, polarizations, and phase relationships. Each photon's path must be anticipated and guided. In this sense, the cloak becomes an instrument for precision rather than secrecy. The more completely we control light, the closer we come to technologies that could transform imaging, communications, and energy. For example, the same techniques used for cloaking can improve antennas, solar cells, and microscopes, allowing light to be confined, concentrated, or dispersed in exact ways. In theoretical physics, the concept of cloaking touches on deeper questions about what it means to see. Vision depends on the interaction between light and matter. But if light can be manipulated perfectly, then visibility itself becomes a property we can engineer. It suggests that what we perceive as reality is not inherent in objects, but arises from how information reaches us. Change that pathway, and the world changes with it. In a way, invisibility research reveals that perception is not absolute, but negotiable. A dialogue between observer and environment mediated by light. There is also a curious symmetry between invisibility and observation at the quantum level. In quantum mechanics, the active measurement affects the system being measured. Perfect invisibility would require interacting with light without disturbing it, a kind of ultimate non-measurement. Yet quantum theory forbids complete non-interaction. Observation and disturbance are inseparable. This connection reminds us that the pursuit of invisibility touches the limits of what it means to exist within a measurable universe. If we were truly invisible, we might also be unobservable, and in a sense undefined. Looking further ahead, researchers have speculated that future cloaking technologies could extend beyond the optical domain. Gravitational or space-time cloaks, though far from realization, have been discussed in theoretical studies. These would manipulate not just light but the propagation of events themselves, hiding occurrences in both space and time. Such ideas remain mathematical curiosities, yet they highlight the unity between optics, relativity, and the broader geometry of the universe. If space-time can be warped to hide matter, perhaps one day the line between invisibility and space-time manipulation will blur completely. Beyond the laboratory, invisibility carries ethical and philosophical weight. It forces us to ask why humans desire it in the first place. The urge to disappear may stem from fear, secrecy, or the wish to transcend limitation. But the scientific pursuit of invisibility is different. It is not about hiding, but about understanding. Each advance in cloaking deepens our command over the fundamental forces that connect us to reality. To make something unseen, we must first see more clearly than ever before. In a broader sense, invisibility research shows how technology can change our relationship with perception. Once to see meant to reveal, now to understand may also mean to conceal. As humanity learns to manipulate waves at will, the boundary between appearance and reality becomes thinner. We begin to realize that the visible world is only one version of the possible, a single interpretation among many. It is easy to view the cloak as a symbol of escape, but it can also be seen as an emblem of humility. Every object, every organism, every star emits or reflects light, declaring its presence to the universe. To become invisible, even temporarily, is to let go of that declaration, to merge with the background, to become part of the continuity rather than the center of attention. In that quiet merging lies a kind of peace, Perhaps this is the true reflection that invisibility offers. In a universe where everything interacts with everything else, total concealment may be impossible, but the desire for it reveals something about consciousness itself, a yearning to step outside of being seen to experience existence without boundary. The pursuit of invisibility mirrors the search for selflessness, a scientific echo of a spiritual idea that to lose the self is to become one with the whole. As the day fades and you drift towards sleep, imagine the gentle flow of light curving effortlessly around you. Not obstructed, not reflected, but guided in harmony. You are neither hidden nor exposed. You are simply part of the pattern. The universe continues to shine, indifferent to who sees or who is seen, and in that indifference lies a strange comfort. Light moves on, endlessly weaving visibility and shadow together, reminding you that to be unseen does not mean to be absent. In the quiet fabric of existence, everything that is remains connected, even when it disappears from view. Chapter 8. Anti-Gravity and Advanced Propulsion. The dream of defying gravity, of lifting effortlessly into the air, freed from the pull of the earth, has haunted human imagination since the first eyes watched birds trace invisible paths across the sky. Flight was the first step toward that dream, achieved not by breaking gravity, but by cooperating with it through aerodynamic lift. Yet the idea of anti-gravity, the notion of neutralizing or reversing gravity itself, remains one of science's most persistent fantasies. Unlike wings or rockets, true anti-gravity would not rely on reaction or thrust. It would rewrite the relationship between mass, energy, and space-time itself. In everyday experience, gravity feels like a force that pulls downward, an invisible weight tethering all things to Earth. Isaac Newton's vision of gravity as an attraction between masses described this pull as an instantaneous connection acting through space. Centuries later, Einstein replaced that idea with geometry. In general relativity, gravity is not a force transmitted through space. It is the shape of space. Matter tells space-time how to curve, and space-time tells matter how to move. Objects do not fall because they are pulled, but because they follow the curved paths of a four-dimensional landscape. If gravity is geometry, then anti-gravity would mean reshaping that geometry in the opposite direction, bending space-time upward where it would normally curve downward. This is no simple reversal. To create an anti-gravity effect, one would need a form of energy that generates repulsive curvature, pushing rather than attracting. In cosmology, we already know of one such phenomenon, dark energy, the mysterious component that drives the accelerated expansion of the universe. Dark energy acts as a kind of negative pressure, stretching space-time apart rather than pulling it together. Yet this effect operates only on the vastest cosmic scales, and its magnitude is far too weak to lift a pebble, let alone a spacecraft. In laboratories on Earth, all known forms of matter and energy produce attractive gravity. Electromagnetism can repel or attract, but gravity, in every observed case, only pulls. The closest analog to repulsive gravity arises from theoretical constructs such as negative mass or exotic energy, both of which remain speculative. A hypothetical object with negative mass would behave in a bizarre way. If pushed, it would accelerate toward the force rather than away from it. Such matter has never been observed, and no known process can produce it stably. Nonetheless, its existence would, in principle, allow for gravitational repulsion, the very essence of anti-gravity. Over the decades, numerous experiments and claims have sought to uncover hints of gravitational shielding or anomalous lift effects, but none have stood up to rigorous verification. From spinning superconductors to charged gyroscopes, devices that allegedly reduced local weight have consistently produced results within experimental error. Gravity has proven remarkably resistant to manipulation. Even at the cutting edge of quantum physics, where forces are unified under deeper laws, gravity remains elusive. It is the weakest of the fundamental interactions, yet it governs the large-scale structure of the cosmos. Its apparent simplicity hides enormous complexity. Modern physics seeks understanding rather than shortcuts. To manipulate gravity, we must first understand how it emerges from the quantum world. Several approaches, such as quantum field theory and curved spacetime and string theory, attempt to explain gravity as an emergent property, the collective behavior of microscopic information encoded on spacetime's boundary. In these frameworks, altering gravity might one day mean adjusting the underlying information of the vacuum itself. But such mastery lies far beyond current technology. We can describe gravity's equations. We cannot yet engineer them. In the meantime, advanced propulsion remains our most realistic path toward overcoming gravity's grip. Conventional rockets work by Newton's third law. For every action, there is an equal and opposite reaction. By expelling mass at high velocity, a rocket pushes itself forward. This mechanism has carried humans to the moon and robotic explorers to the edges of the solar system, but it is limited by fuel. Every kilogram of propellant carried on board must be accelerated, and the faster the exhaust, the more energy it consumes. Physicists and engineers have therefore turned to alternatives that might extend our reach without invoking true anti-gravity. Ion thrusters, for example, accelerate charged particles using electric fields, providing steady, efficient thrust over long durations. Solar sails harness the momentum of photons, gliding on the radiation pressure of sunlight. Nuclear and fusion-based propulsion concepts aim to release energy more densely, producing thrust far beyond chemical rockets. These technologies work with gravity rather than against it, using careful design and energy management to climb out of gravitational wells. Speculative ideas such as the EM drive or other reactionless engines claim to produce thrust without expelling propellant. If true, they would revolutionize propulsion. However, repeated experiments have found no consistent evidence that such devices generate measurable force beyond experimental artifacts. Conservation of momentum, one of the most thoroughly tested principles in physics, remains intact. To date, there is no verified mechanism that allows motion without reaction mass. The laws of physics appear unyielding, and perhaps wisely so. Still, the search for more elegant propulsion continues to inspire. Scientists study gravitational assists, using the motion of planets to accelerate spacecraft without fuel expenditure. They model plasma jets from quasars and black holes, exploring how magnetic fields channel energy into motion at relativistic speeds. In each case, gravity is not defied but used, a reminder that mastery of physics often means cooperation rather than opposition. Even Einstein's theory, when viewed from this angle, offers no true anti-gravity, only the possibility of manipulating curvature through immense energy, an art we are far from practicing. The notion of anti-gravity also touches upon the concept of field unification. If gravity and electromagnetism could be linked under a common framework, perhaps gravitational control would emerge as a byproduct. Some versions of string theory and quantum gravity hint at such relationships, but experimental confirmation remains out of reach. The search for a fifth force, one that modifies gravity on small scales, has so far produced null results. The universe seems content to keep gravity distinct, gentle, and stubbornly consistent. And yet, gravity itself is not a prison. It is the structure that allows stars to form, planets to orbit, and galaxies to dance. Without it, the universe would disperse into featureless emptiness. Anti-gravity, if ever achieved, would not be a triumph over nature, but a rewriting of nature's most essential harmony. To cancel gravity is to erase the geometry that holds the cosmos together. It is a sobering thought that our desire to overcome gravity is, in a way, a desire to transcend the very order that makes existence possible. Still, imagination is not wasted. Anti-gravity research, even when speculative, sharpens our understanding of what is not possible and sometimes reveals unexpected paths forward. The mathematics developed to explore gravitational control feeds into cosmology, satellite dynamics, and the study of inertial frames. The engineering of advanced propulsion systems refines our mastery of plasma, electromagnetism, and energy conversion. Each step, however modest, expands the domain of the possible without violating the laws of physics. In cosmology, the universe itself seems to exhibit a kind of natural anti-gravity on the largest scales. The discovery that cosmic expansion is accelerating implies that space is filled with a form of energy that repels rather than attracts, the same dark energy mentioned before. Though this repulsion is incredibly weak locally, it shows that the geometry of space-time can indeed behave in both attractive and repulsive ways. Perhaps one day, understanding that phenomenon more deeply will allow humankind to manipulate curvature deliberately, shaping gravity as we now shape electromagnetism. For now, such mastery remains a poetic possibility rather than a practical one. Advanced propulsion systems inspired by these ideas may one day take us beyond the limits of chemical fuel. Concepts like fusion rockets, antimatter drives, or light sails powered by powerful lasers point to a future where exploration extends far beyond our solar system. None of these are anti-gravity in the literal sense, but they embody the same longing to move freely among the stars, to loosen the bonds of the world we were born on. Every scientific advance in propulsion is at heart an expression of that ancient human yearning, to rise, to travel, to see what lies beyond. When viewed through the lens of existential reflection, gravity becomes more than a physical phenomenon. It is a metaphor for attachment, the invisible force that binds matter, time, and consciousness together. To dream of anti-gravity is to dream of freedom, but perhaps complete freedom is not what the universe intends. Without gravity, there would be no stars, no warmth, no places for life to emerge. Every attempt to escape gravity's hold is also an acknowledgement of our dependence on it. The same force that keeps us grounded gives us something to rise from. As you drift towards sleep, imagine the world beneath you as a vast cradle of curvature, the ground pulling gently not out of malice but out of kinship. The same geometry that holds you down also binds you to every planet, every moon, every distant galaxy. Gravity is not your enemy, it is your connection to the cosmos. To dream of anti-gravity, then, is not to reject that connection, but to explore its other side, to glimpse what freedom means when nothing holds you, yet everything still belongs to you. Chapter 9. Energy Without Limits, Perpetual Motion and Zero-Point Dreams. Few ideas are more alluring than the thought of limitless energy, a world where machines run forever, where scarcity vanishes, and where motion continues without cost. The dream of perpetual motion is older than modern science itself, a symbol of human defiance against nature's constraints. For centuries, inventors imagined wheels that would spin eternally, fountains that would flow without source, and engines that could drive themselves forever. Yet every attempt, however ingenious, has failed for the same reason. The laws of physics are not suggestions, and energy once spent never returns unchanged. The impossibility of perpetual motion arises from the principles of thermodynamics, those quiet and universal laws that govern all physical systems. The first law states that energy cannot be created or destroyed, only transformed. The second law states that with every transformation, some portion of energy becomes less useful, dispersing into disorder, a measure we call entropy. Together, these laws ensure that every machine, no matter how well designed, must eventually slow, cool, or decay. Energy flows in one direction, from concentrated forms to diffuse ones, from order to equilibrium. The dream of endless motion is, in truth, a misunderstanding of the nature of time itself. Perpetual motion machines fall into two categories. The first kind would violate the conservation of energy by creating work from nothing, producing energy without input. The second kind would respect conservation but evade entropy, converting all energy into useful work without waste. Both are impossible. Friction, resistance, and heat loss are not design flaws, but physical realities. Even the most efficient systems degrade over time because no process is perfectly reversible. The second law of thermodynamics is not a limitation of technology, it is a property of existence. Yet the human fascination with perpetual motion has never faded. Medieval engineers built overbalanced wheels with cleverly arranged weights that promised eternal spin. Renaissance thinkers proposed floating devices that would rise and fall endlessly on self-generated currents. In the industrial age, patent offices were flooded with claims of machines that defied energy conservation. Each design found its downfall in measurement and mathematics. The energy output never exceeded the energy input. The dream persisted not because it was plausible, but because it was beautiful. A vision of eternal vitality in a world governed by decay. Modern physics has replaced that old dream with something subtler. The idea that the vacuum of space itself might hold an inexhaustible energy reservoir. This concept, known as zero-point energy, arises from quantum field theory, which describes empty space not as a void, but as a restless medium of fluctuations. Even at absolute zero, where temperature and motion vanish classically, quantum uncertainty forbids stillness. Fields wiggle, particles briefly appear and disappear, and the vacuum seethes with potential. This is the lowest possible energy state, the 0 point, and it cannot be drained completely. The existence of 0 point energy is not speculative. It has measurable effects. The Casimir effect, for instance, occurs when two metal plates are placed extremely close together in a vacuum. Quantum fluctuations between them differ slightly from those outside, producing a tiny but real force that pushes the plates together. This phenomenon has been verified experimentally and stands as direct evidence that the vacuum is not empty. Yet despite its reality, 0 point energy does not provide an infinite power source. The fluctuations cannot be tapped freely, for any attempt to extract them would require creating an imbalance greater than the energy gained. The vacuum resists exploitation. It gives only what it must and takes back what it lends. Some have speculated that zero-point energy could explain cosmic mysteries such as dark energy, the unknown driver of the universe's accelerating expansion. The energy density predicted by quantum theory, however, exceeds the observed value by an astonishing margin, implying that our understanding of vacuum energy remains incomplete. If the vacuum truly stores energy on such vast scales, it remains hidden from us in ways we cannot yet access. The challenge is not only technological, but conceptual. To harvest zero-point energy would be to alter the ground state of reality itself, an act beyond engineering, touching the foundations of existence. Still, the dream persists in modern guise. Concepts like vacuum energy propulsion or quantum thrusters occasionally appear in speculative research, claiming to exploit the quantum fluctuations that pervade space. None have produced verified results. Each experiment that has claimed to measure thrust without propellant has, when examined carefully, been explained by thermal, magnetic, or vibrational effects. The consensus among physicists remains firm. There is no known mechanism to extract net energy from the vacuum without violating conservation laws. Nature, it seems, keeps her balance sheets immaculate. Yet studying these impossible dreams has deepened science rather than diminished it. The quest to understand why perpetual motion cannot exist led to the formulation of thermodynamics, one of the most powerful frameworks in all of physics. The exploration of vacuum energy has driven advances in quantum theory, cosmology, and particle physics. By confronting impossibility, we learn the structure of reality. Every failure of a perpetual motion design has been a success of understanding. The dream remains, but now it inspires awe rather than pursuit. If we look at the cosmos, we see no exceptions to these rules. Stars shine by burning their nuclear fuel, converting mass into light and heat. Even the sun will one day fade as its reserves are spent. Galaxies radiate energy into the cosmic background, gradually approaching thermal equilibrium. The universe itself trends toward what physicists call heat death, a state of maximum entropy where no more work can be done. This is not a prediction of despair, but of completeness, the natural consequence of the laws that give rise to order in the first place. Still, the idea of infinite energy lingers in the boundaries of theory. Quantum mechanics and relativity both suggest that energy and space-time are intertwined in ways we do not yet fully grasp. The zero-point field might interact subtly with gravity, and some hypotheses propose that the energy of the vacuum contributes to the cosmological constant, the faint pressure that pushes galaxies apart. If that is true, then every cubic centimeter of space holds an invisible ocean of energy, balanced perfectly so that its presence sustains the universe while remaining beyond our reach. The vacuum is not a void, it is a foundation humming quietly beneath all things. When people imagine free energy, they often think of it as liberation from limitation. But physics teaches that limits are what make structure possible. Without entropy, there would be no arrow of time, no evolution, no difference between before and after. Without conservation, the universe would have no stability, no continuity of cause and effect. Perpetual motion fails not because nature is cruel, but because it is consistent. The same rules that prevent infinite energy also protect every pattern we know, from atoms to galaxies. In their balance lies the universe's beauty. The search for inexhaustible energy continues in more grounded forms, through fusion, renewable resources, and efficiency improvements. Each is a reminder that even within constraints, there is room for abundance. Fusion, the process that powers stars, may one day give humanity a near limitless source of clean energy. It will not be perpetual motion. It will be the patient harnessing of the same physics that govern the cosmos. In the end, mastery lies not in breaking the rules, but in learning to dance within them. There is a quiet elegance in the fact that the universe cannot be cheated. Every transformation, every loss, every act of creation obeys the same accounting. The stars burn because their fuel is finite. Life thrives because it feeds on gradients that will one day fade. If energy could flow forever without cost, meaning itself would dissolve. Motion would lose purpose and time would lose direction. In a universe of perfect perpetuity, nothing would begin and nothing would end. It is limitation that gives rise to story. So, as you listen now, imagine the endless ocean of the vacuum, silent, invisible, filled with energy beyond comprehension, yet balanced so precisely that the world remains stable and calm. Every breath you take is powered by ancient transformations of energy, passed down through stars that lived and died before the earth existed. You are not separate from that flow. You are part of it, a brief and radiant expression of motion that cannot last forever and does not need to. The universe is not perpetual, but it is continuous. Its beauty lies not in endlessness, but in renewal. The quiet assurance that even when motion stops, the pattern remains, waiting to begin again. Chapter 10. Tomorrow's Physics, when the impossible becomes routine. Every age believes it stands at the edge of understanding, that the major mysteries have been solved and only details remain. Yet history has shown that certainty is often a prelude to revolution. When Newton described gravity as a universal attraction, few imagined that space itself could curve. When Einstein bent that space into time, no one expected that particles could entangle across galaxies, or that empty space could seethe with energy. Each generation inherits the impossible dreams of the last and quietly turns them into the foundation of daily life. Tomorrow's physics will likely do the same, not by breaking nature's laws, but by discovering new ways to read them. The past century has taught us that the boundaries of possibility shift not through defiance, but through deeper understanding. Concepts once confined to imagination, black holes, antimatter, nuclear energy, quantum computers, have become measurable realities. They remind us that the difference between fiction and physics is often one of time and technique. What today demands exotic conditions or colossal machinery may tomorrow fit within the span of a laboratory bench or even within a handheld device. The physics of the future will not contradict what we know. It will refine and extend it, revealing that impossibility is only a temporary description for what we do not yet comprehend. Many of the breakthroughs awaiting us lie at the intersection of the very small and the very large, the quantum and the cosmic. For over a century, these two pillars of modern physics have stood side by side, complete in their own domains, yet uneasy in their coexistence. Quantum mechanics governs the subatomic, describing probabilities and superpositions. General relativity governs the grand scale of spacetime and gravity. Where they meet, in black holes in the first moments after the Big Bang, their equations conflict. To reconcile them will require a theory of quantum gravity, a framework that unites information, geometry, and energy into a single coherent picture. This pursuit is not merely academic. A unified theory could reveal new forms of matter, new ways to manipulate energy, and perhaps even new insights into the structure of space itself. Technologies born from such understanding might someday make what we call impossible, such as controlled space-time curvature or instantaneous quantum communication, as ordinary as electricity. Yet such visions demand humility. Nature reveals her secrets slowly, often through unexpected detours. Each breakthrough begins not with a grand invention, but with a quiet question. Why does this behave differently? One domain already blurring the boundary between imagination and engineering is quantum information science. What began as an abstract theory about the limits of measurement has become a practical discipline. Quantum computers, once purely theoretical, now perform calculations impossible for classical machines. Quantum networks promise secure communication built on entanglement. The same principles that made teleportation possible for particles may one day link distant processors across continents or even between planets. As our mastery of quantum control deepens, technology will cease to look mechanical at all. It will become probabilistic, adaptive, and self-correcting, much like nature itself. Another frontier is in the control of materials at the atomic scale. The ability to manipulate matter atom by atom has already given rise to nanotechnology, metamaterials, and superconductors that carry current without resistance. Future advances may bring room temperature superconductivity, revolutionizing power distribution and magnetic levitation. The understanding of topological phases of matter, states defined not by symmetry but by geometry, could lead to entirely new forms of electronics. These discoveries reveal a deeper truth. Matter is not a fixed substance, but a pattern of information woven into the quantum field. By changing that pattern, we change reality itself. At cosmic scales, our expanding view of the universe continues to challenge intuition. Observations of dark matter and dark energy show that the familiar atoms making up stars, planets, and living beings compose only a small fraction of existence. The rest remains invisible, detectable only through its gravitational influence. Tomorrow's physics may finally illuminate these hidden components, not as mysterious substances, but as manifestations of deeper laws. Understanding them could explain why the universe expands as it does, how galaxies form, and perhaps whether other universes coexist beyond our horizon. Advanced propulsion and energy systems, though still bound by today's limitations, will evolve from these understandings. We may not achieve anti-gravity, but we may learn to harness gravitational fields for navigation or energy extraction. Fusion power, long the dream of sustainable energy, edges closer to realization with each passing decade. Once controlled, it would offer a nearly inexhaustible power source derived from the same process that lights the stars. The impossible, as always, is merely the undiscovered waiting for method. Yet the most transformative discoveries may come not from vast experiments, but from new ways of thinking. Physics has repeatedly shown that paradigm shifts often begin as questions about the obvious. Why does light always move at the same speed? Why does time seem to flow in one direction? Why does matter exist at all? The next revolution may not be a device or a particle, but a perspective, an idea that redefines what questions are even meaningful. When quantum mechanics emerged, it taught us that observation and reality are intertwined. The next great theory may teach us how consciousness, information, and space-time are connected in ways we only glimpse today. Artificial intelligence and machine learning are already accelerating this process by uncovering patterns in data that human intuition might miss. These tools will not replace discovery, but amplify it, guiding scientists toward regions of mathematical possibility too complex to navigate alone. In this way, human curiosity merges with computational precision, forming a partnership that extends our reach. The boundaries between physics, biology, and computation blur as information becomes the universal language of understanding. Tomorrow's physics will likely change our relationship with the universe as profoundly as relativity changed our view of space and time. But progress will bring new responsibilities. Every tool reshapes the hands that wield it. As we gain control over energy, matter, and possibly space-time itself, we must remember that knowledge is not neutral. The same understanding that allows us to power civilizations can also destroy them. Ethics, philosophy, and science must advance together if we are to navigate a future built on such profound capability. Even the notion of the impossible may evolve. Each discovery reveals that impossibility is often a placeholder for ignorance, a marker for regions where our models fail. To say something is impossible is to say that our understanding is incomplete. History has taught physicists to use the word sparingly. The universe is consistent but not predictable in all its creativity. It delights in revealing loopholes, not through contradiction, but through deeper law. What then might everyday life look like when the impossible becomes routine? Perhaps spacecraft glide effortlessly between planets using fusion or light sails. Perhaps quantum computers design molecules for medicine or materials we have yet to imagine. Perhaps telescopes will peer beyond the cosmic horizon, revealing the geometry of universes adjacent to our own. Or perhaps the greatest revolution will be internal, a new comprehension of reality so profound that it changes how humanity perceives existence itself. Science at its best is not the conquest of mystery, but the partnership with it. The impossible fuels curiosity, and curiosity propels civilization. Even if we never bend space-time or capture vacuum energy, the act of imagining them stretches the boundaries of what we can achieve. The future of physics will not be a final theory written in stone, but an ongoing dialogue between mind and cosmos, a conversation that deepens as our understanding grows. Perhaps this is why physics feels timeless. Every discovery is both an ending and a beginning, a moment when impossibility yields to insight and new impossibilities emerge. The universe remains unfinished, and so do we. Tomorrow's physics will not only expand our knowledge of the world, it will redefine our place within it. We will look back on our present puzzles, dark matter, quantum gravity, entanglement, and see them not as mysteries, but as stepping stones. And when that day comes, the impossible will seem ordinary, and the ordinary will reveal new depths of wonder. The cycle will continue, as it always has, with each generation reaching beyond what came before. For physics, like life itself, is not about reaching an end, but about continuing the journey, learning, questioning, and unfolding in harmony with the universe's endless creativity. So tonight, as you let your thoughts drift beyond the horizon of what is known, remember that every impossible dream begins as a question whispered into the silence. Somewhere far beyond the limits of current understanding, the answers already exist, waiting for the courage of future minds to uncover them. The universe is patient. It unfolds only as quickly as we dare to imagine it. And as long as there are those who still ask, what if, tomorrow's physics will never stop becoming today's reality. If you're still awake, my friend, there's another journey waiting for you. You can keep drifting through the cosmos. Just choose another video and keep exploring while you rest. And if your eyes are already closing, then sleep well and dream among the stars.